Design RAG architecture. Hello, everyone. Today, I'd like to walk through how to design a RAG architecture in system design. RAG stands for Retrieval-Augmented Generation. The key idea is simple. Retrieve relevant knowledge, add it to the prompt. Let the LLM generate an answer. But in real systems, RAG is not just adding a vector database to an LLM. It is a full pipeline that prepares data, retrieves the right context, and helps the model generate more accurate and grounded answers. Now let's start with the core framework. When I think about RAG architecture, I usually break it down into 4 parts. First, the offline ingestion pipeline. Second, embedding and indexing. Third, the online retrieval and context construction pipeline. And finally, generation, validation, and evaluation. The main trade-off is recall versus precision versus latency versus cost. Why do we need RAG? Because LLMs alone have limitations. They may not know private company data. Their knowledge may be outdated. They can hallucinate. And they cannot directly search through a large internal document corpus. RAG solves this by grounding the model's answer in external knowledge at runtime. Instead of asking the model to answer from memory, the system first retrieves relevant documents and gives them to the model as context. So the key idea is this. RAG improves factuality by grounding generation in retrieved knowledge. A RAG system usually starts with an offline pipeline. The flow looks like this. Raw documents go through cleaning, then chunking, then metadata extraction, then embedding, then indexing into a vector database. The most important step here is chunking. Instead of storing one huge document, we split it into smaller chunks, usually a few hundred tokens each. Chunking matters because retrieval happens at the chunk level. If chunks are too small, they may lose context. If chunks are too large, they may add noise and increase token cost. We also attach metadata, such as document ID, source, section, timestamp, and permission information. Metadata helps with filtering, freshness, access control, and citations. Then each chunk is converted into an embedding, which is a vector representation of text. The vector database stores the embedding, the text chunk, and the metadata. The key idea is this. Good RAG starts with good data preparation and good chunking. At query time, the online pipeline starts. The flow looks like this. The user query is converted into a query embedding. Then the system retrieves the top K chunks. Then it re-ranks the results. Then it builds the context. Then it sends the final prompt to the LLM. First, the user query is converted into an embedding. Then the system searches the vector database for the most similar chunks. This is semantic search, but semantic search alone is not always enough. For exact terms like error codes, product names, IDs, or policy names, keyword search can work better. That is why many production systems use hybrid search, combining semantic search with keyword search. After retrieval, we often use re-ranking. For example, the system may retrieve the top 50 candidates, re-rank them, and then keep the top 5 chunks. Retrieval focuses on recall, re-ranking improves precision, then the system builds the final context. It cannot pass every retrieved chunk to the model because the context window is limited, so the system must deduplicate, rank, truncate, and format the context into the prompt. The key idea is this. Retrieval finds candidates. Context construction decides what the model actually sees. After context construction, the LLM generates the answer. The prompt should tell the model to answer based only on the provided context. If the answer is not in the context, the model should say it does not know, but we should not blindly trust the output. The system should validate the answer, attach citations, check safety, verify source support, and retry or fallback if needed. Evaluation is also important. For retrieval, we measure things like recall at K, precision, and context relevance. For generation, we measure answer accuracy, faithfulness, citation quality, latency, cost, and user satisfaction. The key idea is this. RAG quality depends on both retrieval quality and generation quality. RAG design has several important trade-offs. Retrieving more documents improves recall, but may add noise and increase latency. Using larger chunks preserves more context, but increases token cost. Using re-ranking improves quality, but adds latency and cost. Common failure modes include irrelevant retrieval, missing key documents, outdated data, context overflow, hallucination, and prompt injection through retrieved documents. So, to summarize, RAG is not a single step. It is a full pipeline. Offline, we prepare and index knowledge. Online, we retrieve relevant chunks, build context, call the LLM, validate the answer, and return sources. The final insight is this: RAG architecture is not about adding a vector database. It is about designing a reliable retrieval and context pipeline around the LLM. In RAG systems, the model can only answer well if the system gives it the right context. Thank you.